In the time it takes to listen to this sentence, light will have traveled nearly 900,000 kilometers. Our deepest radio surveys have scanned that same vast distance and heard nothing. The universe has 4 billion years to respond. It chose silence. But the most disturbing possibility is not what the universe may one day become. It is that this silence already surrounds us, while our civilization still does not understand what that silence truly means. Tonight, we will follow a single disturbing chain of reasoning, from the observable fact of cosmic silence through every explanation that seems to resolve it, the one conclusion that cannot be reasoned away, and discover why the emptiness of the universe may be the most important message ever sent to our species. Before we dive in, if you love exploring the deep mysteries of the cosmos as much as we do, take a second to like the video or subscribe and tell me where you're listening from and what time it is. Now, let's begin. Picture the night sky as it looked to a shepherd 3,000 years ago, standing on a hillside somewhere in what we now call the Fertile Crescent, that arc of cultivable land curving from the eastern edge of the Mediterranean through the valleys of the Tigris and Euphrates. The shepherd tilts his head back. Above him, the Milky Way spreads like a river of pale fire across the darkness, a density of light so thick it creates its own geography in the sky. He has no concept of what those lights are. He knows they move in patterns. He knows they return. He has woven stories around them, gods, animals, heroes frozen in the act of dying. But he does not know, cannot know, that each point of light is a furnace of nuclear fire incomprehensibly larger than the world he stands on. Now walk forward in time to the 20th century. By then, we know what the stars are. We know they are suns. We know that many of them, perhaps most of them, are orbited by planets. We know that the laws of chemistry operating on Earth, carbon bonding to carbon, water dissolving minerals, energy cascading through molecular gradients, are not local peculiarities. They are universal. The same atoms exist everywhere. The same rules apply. And so, at some point in the mid-20th century, the question that had always been theological became, for the first time, scientific. If the stars are suns, and suns have planets, and the laws of chemistry are universal, then where is everyone? This is the question. It sounds simple. It sounds almost naive, the kind of question a child might ask. And the fact that after more than 60 years of serious scientific effort, we still cannot answer it with certainty. That fact alone should keep you awake at night. In 1950, the physicist and Nobel laureate Enrico Fermi famously posed the question to his colleagues. Where are they? Fermi had been thinking about the age of the galaxy, about the billions of years available for civilizations to arise and spread, and the logic seemed inescapable. With an almost unfathomable number of stars and planets in the universe, it seemed obvious that intelligent civilizations capable of developing radio astronomy and interstellar travel should pepper the distant stars. Yet no evidence of such civilizations existed. The question was less an argument than a gesture, a pointing finger aimed at a sky that should have been full of answers and was, instead, completely empty. The silence, that day at Los Alamos, was understood as a puzzle, something to be solved eventually with better instruments and more patience. It would take decades for the full weight of that silence to become apparent, and it would take the work of many researchers across many disciplines to reveal that the silence is not simply a gap in our knowledge. It may instead be a message. Stay with that for a moment. The silence is the message, not the absence of a message, the message itself. The Fermi paradox, is the discrepancy between the lack of conclusive evidence of advanced extraterrestrial life and the apparently high likelihood of its existence. But to understand why the paradox is genuinely disturbing and not merely a curiosity for astronomers, we need to build the full picture from the ground up. We need to understand how large the universe actually is, how long it has existed, how many opportunities for life it contains, and how thoroughly we have searched for signs of it. Only then can we appreciate what the silence actually means. The observable universe, the portion of the cosmos from which light has had enough time to reach us in the 13.8 billion years since the Big Bang, is a sphere roughly 93 billion light-years in diameter. That number is essentially meaningless to a human brain, and deliberately so. It was not designed to be comprehended. What we can do is work with the structures within it. The targets of major SETI programs include 1 million nearby stars and the centers of 100 galaxies. But the universe contains vastly more. Current estimates place the number of galaxies in the observable universe at roughly 2 trillion. The Milky Way alone contains somewhere between 100 billion and 400 billion stars. Each of those stars, based on observations from instruments like the Kepler Space Telescope, is orbited on average by more than one planet. Do the arithmetic. The number of planets in the observable universe is, by any conservative estimate, measured in the hundreds of sextillions. A sextillion is a 1 followed by 21 zeros. Most of those planets are inhospitable to life as we understand it. They are gas giants, or ice worlds, or scorched rocks orbiting too close to their stars. But even if only 1 in a billion of them develops conditions suitable for life, the number remaining is still beyond meaningful comprehension. And the universe is old, profoundly old. The stars that formed in the earliest epoch of stellar formation, the so-called population 3 stars, enormous and short-lived, burned out before our sun even existed. Smaller, longer-lived stars have been burning for 10 billion years. If life requires roughly 4 billion years to progress from simple chemistry to technological civilization, as it apparently did here on Earth, then civilizations arising around older stars could be 4, 5, or 6 billion years more advanced than we are. 6 billion years of additional development. It is genuinely impossible to imagine what a civilization might accomplish in 6 billion years. We went from the first controlled flight at Kitty Hawk to the first moon landing in 66 years. Extrapolate that trajectory across a billion years, and you begin to approach the kind of capabilities that should, by now, be detectable anywhere in the galaxy. Should be. And yet. Pause here, because this is the first place where the argument starts to bite. The galaxy is approximately 100,000 light-years across. Even if it took the same inordinate amount of time for an alien civilization to make the technological leaps humanity has, given the age of the universe, there should be at least a few interplanetary species colonizing their entire galaxy by now. Even at a tiny fraction of the speed of light, say 1%, a civilization could cross the full width of the Milky Way in 10 million years. 10 million years sounds like a very long time. Against the backdrop of the galaxy's age, it is a rounding error. A civilization that began expanding 1 billion years ago, expanding slowly, taking its time, resting for millions of years between jumps, would have had more than enough time to visit, or at least signal, every single stellar system in the Milky Way hundreds of times over. Astronomers see no evidence of such civilizations. When they look to the stars, the silence is deafening. This is not a failure of instrumentation. It is not a limitation of our radio telescopes or our optical surveys. The absence we are confronting is not of the subtle, ambiguous variety that might be explained away by technological inadequacy. Breakthrough, listen, described as the most comprehensive and systematically designed search for extraterrestrial techno-signatures to date, encompasses both radio and optical domains, and leverages a global network of leading telescopes, custom digital instrumentation, and advanced data analysis pipelines. With $100 million in funding and thousands of hours of dedicated telescope time on state-of-the-art facilities, it is the most comprehensive search for alien communications to date. And what has this unprecedented effort returned? Upon algorithmic processing, correlation of signal characteristics with known radio frequency interference populations, and extensive visual inspection, researchers found no compelling evidence of technosignatures. Nothing. Not a whisper. While researchers found no technosignatures of civilization, the analysis and other detailed studies the Breakthrough Listen group has conducted are gradually putting limits on the location and capabilities of advanced civilizations that may exist in our galaxy. Those limits are increasingly stringent. Results suggest that fewer than roughly 0.1% of stellar systems within 50 parsecs possess the type of transmitters searched in such surveys. And that is only within our immediate cosmic neighborhood. The surveys have extended further. Null results set the most stringent upper limits to date on the prevalence of high-power artificial transmitters in the universe. The textbook answer to this is that we simply have not looked hard enough. Space is large, our instruments are young, and our search has barely scratched the surface of what needs to be examined. This is the reassuring version. This is the version that allows us to go to sleep feeling comfortable. And it is not entirely wrong. As researcher Jason Wright at Penn State estimated, if the world's oceans represented every place and wavelength we could search for intelligence signals, we have, to date, explored only a hot tub's worth of it. But here is what that reassuring framing conceals. The argument for cosmic life is not primarily based on what we have searched for. It is based on the statistics of what should be there. And the statistics are overwhelming. The numbers are so large, the timescales so vast, the chemistry so universal that even accounting for every limitation and uncertainty, the silence we observe is far quieter than our models of the universe predict. Something is wrong. The universe should be loud. The universe should be full of signals, megastructures, and evidence of engineering on cosmic scales. An ancient civilization, one even 1 billion years older than us, would, by now, have had time to restructure entire star systems, to harvest stellar energy, to deploy instruments capable of being detected from across the galaxy. The theoretical physicist Freeman Dyson suggested in 1960 that an advanced civilization might encase its home star in a shell of collectors to harvest every photon of energy the star produces, what has since been called a Dyson sphere, and that such a structure would produce a distinctive infrared signature detectable across interstellar distances. We have looked for Dyson spheres. We have found none. The universe is quiet. It is profoundly, completely, disturbingly quiet. And that quiet is not a neutral fact. It is data. It tells us something. Something about what happens to civilizations. Something about what the universe does to intelligence when it arises. The question is, what does it tell us exactly? And this is where the real investigation begins. Because before we can interpret the silence, we need to close every possible innocent explanation for it. We need to ask, with genuine rigor, is it possible that we are simply alone? That the silence means nothing more than the fact that complex life is extraordinarily rare, and we are its only current expression in the observable universe? The answer to that question will take us through the Drake equation, through the chemistry of life's origins, through the history of Earth's nearly catastrophic near misses, and eventually to a doorway that opens onto something deeply unsettling. Something that concerns not just the fate of civilizations out there, but the fate of the one civilization we can actually observe from the inside. The concept of the Great Filter originates in economist Robin Hanson's argument that the failure to find any extraterrestrial civilizations in the observable universe implies that something is wrong with one or more of the arguments that the appearance of advanced intelligent life is probable. This observation is conceptualized in terms of a barrier which acts to reduce the great number of sites where intelligent life might arise to the tiny number of intelligent species, with advanced civilizations actually observed, currently just one, human. One. Of the hundreds of sextillions of possible worlds, the count of confirmed communicating civilizations stands at one. That number, that solitary, extraordinary, troubling number, is where everything begins. To understand why the silence is so strange, we first need to understand why the universe should, by every reasonable expectation, be anything but silent. And that means spending time with the Drake equation, the framework that, since 1961, has structured our thinking about the probability of cosmic company. Formulated by astronomer Frank Drake in 1961, the Drake equation is a probabilistic argument that estimates the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It considers factors like the rate of star formation, the fraction of those stars with planets, and the likelihood of life developing. The equation expresses the number of active communicating civilizations as the product of a chain of probabilities. How many new stars form each year? How many have planets? How many of those planets are potentially habitable? What fraction of habitable planets develop life? What fraction of those develop intelligence? What fraction of intelligent species develop technology and broadcast their existence? And finally, how long such a technological civilization typically lasts before going silent. When Drake first presented this framework at the National Radio Astronomy Observatory in Greenbank, West Virginia, in 1961, at a meeting that became the founding moment of modern SETI. The early factors in the equation were already beginning to look favorable. And in the decades since, they have continued to look more and more favorable in ways that make the silence progressively harder to explain. The rate of star formation in the Milky Way, well established. Estimates range from roughly 2 to 7 new stars born in our galaxy every year. The fraction of those stars with planets, we now know, thanks to the Kepler Space Telescope and its successors, that planets are essentially universal. Most stars have them. The fraction of planets in the habitable zone, close enough to their star for liquid water, far enough to avoid being scorched, smaller but still substantial. We have now confirmed thousands of exoplanets in what astronomers call the habitable zone, and the total number of potentially habitable worlds in the Milky Way alone is estimated in the billions. To date, more than 6,200 exoplanets have been confirmed in over 4,800 planetary systems, with thousands more awaiting confirmation. The first 4 factors of the Drake equation, star formation rate, fraction with planets, fraction with habitable worlds, converge on a picture of a galaxy teeming with potentially life-bearing real estate. If you inserted only the best supported, most conservative estimates for these early terms, you would calculate that the Milky Way contains somewhere between 1 billion and 10 billion potentially habitable planets. That is just our galaxy. There are, by current count, roughly 2 trillion galaxies in the observable universe. And this is where the equation runs into the wall. Because the remaining terms, the fraction of habitable planets that develop life, the fraction of life-bearing planets that develop intelligence, the fraction of intelligent species that develop communicating technology, and the length of time such civilizations persist. these terms are not well constrained. They vary in the literature by dozens or even hundreds of orders of magnitude. And that uncertainty is not a superficial problem. It is, arguably, the most important unsolved problem in science. Consider the first of these uncertain terms, the fraction of habitable planets on which life actually arises. On Earth, life appeared astonishingly fast. The oldest confirmed microfossils date to approximately 3.5 billion years ago, just over a billion years after Earth formed, and during a period when the planet was still being bombarded by asteroids and was, by any reasonable measure, barely habitable. Life did not wait for conditions to be comfortable. It erupted almost immediately. Some researchers interpret this speed as evidence that life is not just possible, but nearly inevitable. That given liquid water, the right mix of organic molecules, and a supply of energy, chemistry will, with something approaching certainty, organize itself into self-replicating systems. The chemist Lee Cronin at the University of Glasgow has spent years developing what he calls assembly theory, a framework for measuring the complexity of molecular structures as evidence of biological origin. And his work points toward life as a predictable outcome of chemistry under the right conditions. If Cronin and those who share his intuition are correct, then the galaxy should be biologically rich beyond imagination. But others look at the speed of life's emergence on Earth and see not evidence of inevitability, but evidence of selection bias. We are here to ask the question, and we can only ask it from a planet where life arose. Of course, life arose quickly on our planet. If it had not, we would not exist to notice. This is the anthropic principle, and it cuts both ways. It can make even extraordinarily rare events appear, from the inside, to be commonplace. Almost all arguments involving the Drake equations suffer from the overconfidence effect, a common error of probabilistic reasoning about low-probability events, by guessing specific numbers for likelihoods of events whose mechanism is not understood. An analysis that takes into account some of the uncertainty associated with this lack of understanding, carried out by researchers Anders Sandberg, Eric Drexler, and Toby Ord, suggests that there is a substantial ex-ante probability of there being no other intelligent life in our observable universe. Some researchers think the filter is behind us. Others think it lies ahead. This disagreement is not merely academic. It may be the most consequential question in human history. And its answer, if it has one, is embedded in the silence. What we can say with confidence at this point in the investigation is this: the universe is either deeply, mysteriously empty of intelligence, or intelligence exists out there and is, for reasons we do not understand, completely invisible to us. Both possibilities are disturbing. Both demand an explanation. And the work of finding that explanation, of following the logic wherever it leads, is what the next hours of this exploration are devoted to. Take stock of where we are. We began with an observation. The universe is silent. We established that this silence is not a technological limitation, but a genuine empirical puzzle. That the universe, by every statistical expectation, should be full of detectable civilizations, and is not. And we introduced the Drake equation as the framework within which this puzzle has been formally studied since 1961. We have seen that the early, well-constrained terms of the equation paint a picture of a cosmos rich in potentially life-bearing worlds. And we have seen that the late, poorly constrained terms are where the argument either opens into wonder or collapses into dread. Now we turn to those late terms, and we begin with the one that is most likely to carry the answer and the most likely to carry the danger. So we have arrived at the concept that will anchor everything that follows. It is the idea proposed by the economist Robin Hanson in 1996, an idea so simple in structure and so devastating in implication that it has become, for many researchers who work on questions of cosmic life, the single most important framework ever developed for thinking about our place in the universe. That number, currently, is 1. The argument is deceptively clean. We observe a silent universe. The silence implies that something, some step or series of steps in the long chain from chemistry to civilization, is extraordinarily improbable. Something filters out civilizations before they become visible. That filter might be in our past. It might be ahead of us. Read that again, slowly. The more likely it is that complex life arises commonly across the universe, the more likely it is that humanity is doomed. The more likely it is that the difficult steps are ahead of us rather than behind us, the darker our future becomes. This is the central horror of the Great Filter. It is not a horror of cosmic scale or remote possibility. It is a horror that lives inside the logic of a single question. How hard was it to get here? If it was extraordinarily hard, if abiogenesis is impossibly rare, or if the evolution of complex cells is a 1 in a trillion event, then we are probably safe, because the filter is behind us, and we are a statistical miracle. But if it was not that hard, if life arises readily, if intelligence follows naturally from biological complexity, then the filter is almost certainly ahead of us, and it is enormous, something enormous and silent and waiting. Finding life on Mars would not be a celebration. Philosopher Nick Bostrom at Oxford University stated this with characteristic directness. He hoped Mars probes would find nothing. Stay with that for a moment. The discovery of a fossil bacterium on Mars, what would, in most public framings, be hailed as the greatest discovery in human history, would, according to the logic of the Great Filter, be a catastrophic omen. It would mean that the early steps were not the filter. It would mean that the filter still lies ahead of us, between where we are now and the stars. This is where the silence of the universe begins to carry weight in a very personal way. The question is no longer, are we alone? The question becomes, which version of not alone would we prefer? And the answer, disturbing as it is, turns out to be, we should hope to be more alone than we currently fear. That is the architecture of the problem. That is the shape of the thing we are investigating. Now we need to examine the individual components of the Great Filter, each possible candidate, each step in the evolutionary chain that might be the true bottleneck, and assess how much explanatory power it carries. Because the answer to where the filter lies will determine everything about how we should think about the future of this civilization. Take stock of where we are. We have established the Fermi paradox as a genuine empirical puzzle, the silence of the universe, measured against the statistical certainty that it should not be silent. We have introduced the Drake equation as the framework within which this problem is formally studied, and we have noted that the early, well-constrained terms paint a picture of a cosmos rich in potentially life-bearing worlds. We have introduced the Great Filter as the logical response to the paradox, the idea that somewhere in the long chain from chemistry to civilization, at least one step must be extraordinarily improbable. And we have established the central disturbing asymmetry of the filter. The better the news at the beginning of the chain, the worse the news at the end. Now we turn to the candidates, the steps that might be the filter. We examine them one by one, in the order in which they occur in biological history, beginning with the very first step, the one that nobody fully understands, and whose probability remains one of the most debated and consequential unknowns in all of science. The origin of life from non-living chemistry. Picture a world with no life. Not a dead world in the sense we use today. Not a world stripped of what it once had. A primordial world, 4 billion years ago. A young planet that has barely cooled from the violence of its formation. The sky is a strange color, tinged with methane and ammonia and carbon dioxide in ratios utterly unlike anything breathed today. The ocean is warm and shallow in many places, rich with dissolved minerals and organic molecules, delivered partly by the constant rain of asteroids still pelting the inner solar system. Hydrothermal vents on the ocean floor pump hydrogen and heat into the water. The surface is regularly illuminated by lightning discharges in the thick atmosphere above. The raw materials for complexity are everywhere. And yet, there is no life. There is chemistry, energy, and time. But there is no life. Then, at some point, perhaps quickly, perhaps slowly, something changes. Some collection of molecules achieves a property that no non-living thing has ever achieved. It makes copies of itself. It replicates. It persists. And in persisting, it begins the 4 billion year process that eventually produces, among other things, you. This sounds orderly when described as a sequence. In reality, each step in that sequence is a problem that chemists and biologists have been working on for decades without arriving at consensus. This is not a minor admission. This is perhaps the most consequential gap in our scientific understanding of natural history. We know what life requires. We know what the early Earth provided. We do not know how the gap between them was bridged. The Miller-Urey experiment in 1953, conducted by chemists Stanley Miller and Harold Urey at the University of Chicago, showed that amino acids, the building blocks of proteins, could be synthesized under conditions thought to resemble early Earth's atmosphere. This was considered a landmark result, suggesting that the basic molecular ingredients of life were not mysterious or exotic, but could form spontaneously from simple chemistry. For several decades, this was taken as partial evidence that life's origin was not improbably difficult. But the amino acid gap is enormous. Making amino acids is a long way from making a cell. The gap between a molecule and a functioning self-replicator, a molecule that can copy itself, enclose itself in a protective membrane, regulate its own chemistry, and maintain the distinction between inside and outside, is an abyss of complexity. The problem is not merely chemical, it is informational. A living cell is not just a collection of molecules in the right ratios. It is a system of extraordinary organized information, where the sequence of molecular components matters as much as their presence. The probability of assembling the correct informational sequence by random chemistry is, depending on assumptions, extraordinarily small. Some researchers think this improbability is the filter. Specifically, they argue that abiogenesis, the spontaneous emergence of life from non-living chemistry, is so improbable that it occurs across the entire universe only a vanishingly small fraction of the time, even on planets that otherwise meet all the physical requirements for habitability. Under this view, the universe is indeed full of warm, wet, chemistry-rich worlds. But on most of them, the dice simply never come up showing life. The universe is a casino where nearly everyone at the table loses. Others think the speed of life's emergence on early Earth argues against this view. If abiogenesis were that improbable, they suggest, why did it happen so quickly on Earth, within a few 100 million years of the planet cooling sufficiently to allow liquid water? The apparent speed of life's first appearance seems to indicate a chemical process that, under the right conditions, proceeds with something approaching inevitability. But here's what that argument doesn't account for: the anthropic principle. We are, by definition, in a world where life arose. We cannot sample the worlds where it did not. If even one world in a billion produces life after a billion years of trying, and we can only ever observe a world where life arose quickly, then the speed of life's appearance here tells us very little about how probable the event was in the broader universe. It is an observation entirely consistent with extreme rarity, viewed from the only vantage point available to us: a sample size of 1. That phrase alone should arrest the mind. All of science works by comparing samples, by looking at many instances of a phenomenon and identifying patterns. The origin of life, as far as we can currently confirm, has one instance in the observable universe, one data point from which to draw a probability estimate. The uncertainty attached to that estimate is not a small technical caveat. It is the dominant feature of the problem. Hundreds of orders of magnitude. The range of reasonable estimates for the probability of abiogenesis spans a range so vast that numbers at the lower end are essentially zero, and numbers at the higher end approach certainty. This is not a debate about decimal places. It is a debate about the fundamental nature of life's relationship to chemistry. And it has not been resolved. Sandberg, Drexler, and Ord, working at Oxford's Future of Humanity Institute, approached the problem differently from their predecessors. Rather than inserting best guess numbers into the Drake equation, they asked, what happens when you honestly account for the full range of uncertainty in each parameter? The answer was startling. When the uncertainty in the biological terms is handled rigorously, when you allow the probability of abiogenesis to range from vanishingly small to nearly certain. The probability of Earth being alone in the observable universe is not negligible. It is, in fact, substantial. Some researchers find this analysis persuasive. Others argue it underestimates the probability of abiogenesis by treating an unknown mechanism as if it were likely to be inefficient. The debate continues in the literature, unresolved, and will remain unresolved until either we detect extraterrestrial life or we synthesize life from non-living chemistry in the laboratory. An experiment that, if successful, would constitute the most important result in the history of science. We have not yet succeeded. What we can say with confidence is this: abiogenesis is either a filter or it is not. If it is the filter, if chemistry fails to produce life on the overwhelming majority of suitable planets, then this wide universe is probably empty for a reason that is, in a sense, reassuring. The filter is behind us. We won the lottery, and the silence of the sky is simply the lottery's normal output. Most planets are lost. But there is a second possibility, one that is harder to dismiss and harder to endure. The second major candidate for the position of great filter lies not at the origin of life, but roughly 2 billion years later, in one of the most important and least discussed events in biological history, the emergence of the eukaryotic cell. For most people who think about evolution, the story of life follows a familiar arc, from simple chemistry to bacteria, from bacteria to more complex organisms, from complexity to multicellularity, from multicellular life to intelligence. The transitions seem, in retrospect, almost inevitable. One thing leads to another. Complexity builds on itself. But this view, the textbook picture of life's gradual escalation, conceals something deeply strange about the actual history of life on Earth. For roughly 1.5 to 2 billion years after life first appeared on this planet, an interval longer than the entire history of multicellular life, nothing of structural significance happened. Life remained stuck at the level of single-celled organisms with no internal compartmentalization. Prokaryotes, bacteria and archaea, ruled the Earth and ruled it absolutely. They diversified in terms of chemistry. They occupied every available environmental niche. But they did not develop nuclei. They did not develop complex internal structures. They did not progress toward complexity in any meaningful architectural sense. Once, in 1.8 billion years, on a planet covered with single-celled life, the transition to eukaryotic cells appears, according to current evidence, to have happened just once. And that single event, that single, unrepeated, extraordinary transition, produced every animal, every plant, every fungus, every organism of any complexity that has ever existed on Earth. Every one of them traces its lineage to that one moment when one prokaryote engulfed another, and instead of digesting it, somehow formed a stable symbiotic partnership that eventually became the mitochondria-bearing, nucleus-possessing eukaryotic cell that is the foundation of complex life. The biologist Lynn Margulis first proposed this endosymbiotic theory in 1967. For years, it was considered fringe. By the 1980s, the accumulating molecular evidence had made it the accepted explanation. The mitochondria in every cell of your body are, in origin, bacteria. Separate organisms captured or captured by an ancient archaeal host and eventually integrated so completely that they can no longer exist independently. Every complex cell is, at its deepest level, a colonial entity, an improbable coalition that should not have worked. It worked once. And we have no explanation for why it should have worked even that many times. The argument is essentially statistical and architectural. The transition from prokaryote to eukaryote requires a specific kind of accidental symbiosis under specific conditions. And the fact that this transition appears to have occurred only once in 4 billion years of Earth's biological history suggests it is extraordinarily improbable. If eukaryogenesis is the filter, then the universe may be genuinely rich in microbial life, in bacterial and archaeal ecosystems, thriving in the warm water pockets of moons like Europa and Enceladus, on the subsurface oceans of distant planets, even perhaps in the atmospheres of gas giants. Simple life may be everywhere, but simple life does not build radio telescopes. Simple life does not develop language. This possibility has a specific texture to it. It is not the cold emptiness of a universe where life never began. It is something more intimate and more melancholy, a universe rich with biology that never managed to be interesting. An ocean full of invisible film, cell by cell, consuming chemical gradients and dividing and dying on a billion worlds, never communicating, never accumulating knowledge, never doing anything that would be visible from 40 light years away. Consider what this would mean for our search. All the instruments we have trained on the sky, all the radio telescopes and optical interferometers, all the spectroscopic surveys looking for biosignatures in planetary atmospheres are, in principle, sensitive to complex life, to the metabolic byproducts of complex organisms, to the technological signatures of civilizations. To bacteria? Almost certainly not. The biosignature of a bacterial mat on the surface of an ocean is almost indistinguishable, at interstellar distances, from abiotically produced chemistry. Bacteria, even if they fill the universe, would be effectively invisible to us. So if eukaryogenesis is the filter, the silence we observe is not the silence of a biologically empty universe. It is the silence of a universe that stopped at the wrong step. That is one interpretation. Some researchers find it compelling. Others are less convinced. The key phrase there is, given enough time. The question is whether the universe provides enough time. For planets orbiting long-lived stars, the small dim red dwarfs that constitute approximately 70% of all stars in the galaxy, the available time is theoretically immense. Some red dwarf stars will burn for trillions of years. On their planets, if those planets are habitable, evolution would have available periods of time that dwarf what Earth has experienced by factors of hundreds. Does more time mean more eukaryotes? Perhaps. Or perhaps the eukaryotic transition requires not just time, but a very specific set of conditions. A particular ratio of oxygen in the atmosphere, a particular mineral composition in the ocean, a particular kind of cellular crowding that creates the chemical opportunity for endosymbiosis to occur. Perhaps the transition is not merely improbable, but conditionally improbable. Rare not just on any given world, but specifically rare in the conditions that Earth's geological history provided. We cannot know. This is the first place where our investigation reaches a genuine epistemological wall. It is not that we do not yet have the answer. It is that we cannot currently identify the experiment that would give us the answer. We have one data point, Earth. And Earth's evolutionary history is consistent with multiple probability estimates spanning many orders of magnitude. The wall is not a temporary obstacle. It may be permanent. What we can say is that eukaryogenesis, wherever it falls in terms of probability, represents a genuine and significant candidate for the filter. It is the kind of event that, had it not occurred on Earth, would have guaranteed a biologically active but permanently invisible planet. Inhabited, silent, permanently stuck. There is a third candidate, more recent in geological time but no less extraordinary in its implications for the Great Filter. It is not a single transition, but a convergence of transitions, all occurring within a window of roughly 500 million years that transformed the history of multicellular life on Earth. The moment that complex animals, organisms with muscles and nervous systems and eyes, appeared in what geologists call the Cambrian explosion. And the deeper question beneath that explosion, how many times would you expect it to happen on a world that had spent 3 billion years accumulating single-celled life? Picture the Pilbara region of Western Australia. The landscape is ancient, one of the oldest exposed rock formations on Earth, with rocks dating back more than 3 billion years. In those rocks, in microbial mat fossils deposited in shallow coastal seas, we can trace the unbroken lineage of life at its simplest. Thin films of biological activity, stratified in sediment, unchanged in any fundamental way across vast stretches of geological time. The biosphere of early Earth was not diverse in any architectural sense. It was a continuous, global microbial monotony. The transition away from that monotony did not happen quickly. It happened in geological slow motion, and it required a series of steps. The evolution of sexual reproduction, the development of multicellular body plans, the invention of hard structures like shells and skeletons, the development of predation, and the consequent evolutionary arms race that drove complexity upward with frightening speed once it began. Each of those steps could, individually, be the filter. Sexual reproduction is a particularly strange candidate because its evolutionary logic is counterintuitive. A sexually reproducing organism passes only half its genetic material to each offspring. An asexually reproducing organism passes all of it. From a simple arithmetic perspective, sexual reproduction should be selected against. It is a 50% reproductive penalty per generation. And yet, it has proven to be one of the most powerful engines of evolutionary diversification in the history of life. The question of why sexual reproduction evolved at all Why organisms with the option of asexual reproduction would ever adopt a mechanism that halves their reproductive efficiency remains genuinely contested in evolutionary biology. Only once. Again and again in the catalogue of evolutionary transitions, we encounter this phrase: the eukaryotic cell, once. Multicellularity, once. Or, more precisely, the kind of multicellularity that leads to complex animals happened in a single lineage, though simpler forms of multicellularity evolved independently in algae and fungi. Complex nervous systems. The animal nervous system, with its architectural plan of neurons and synapses and the brain as a central integrating structure, evolved in a single lineage. Eyes evolved independently, perhaps 40 to 60 times, across different animal lineages, suggesting that certain solutions to physical problems do converge. But the specific architecture of the vertebrate brain, with its capacity for abstract thought and language and planning, does not appear to be a convergent solution. It appears to be an accident of a specific lineage's specific history, and language itself. Language, the ability to transmit information symbolically across generations, accumulating knowledge in a way that no other species manages. This is the step that transforms a clever animal into a technological civilization. This is the step that produces radio telescopes and spacecraft, and the question, where is everyone? And in 4 billion years of life on Earth, it happened once. Some researchers are skeptical that this rarity is meaningful. They point to the general principle of convergent evolution, the way that natural selection tends to independently arrive at similar solutions to similar problems across different lineages, and suggest that intelligence, like eyes, might be a convergent outcome of complex nervous systems under suitable environmental pressures. Under this view, the evolution of intelligence is something like an inevitable consequence of ecological competition and predation pressure, a solution that natural selection discovers wherever the conditions allow. Others are less optimistic. They point to the fact that on Earth, intelligence has been available as an evolutionary option for hundreds of millions of years, since the Cambrian nervous systems have existed, and that, in all that time, only one lineage ever arrived at language and technology. Dinosaurs dominated the Earth for roughly 160 million years. Dragonflies have existed for 300 million years. Sharks have existed for 400 million years. None of them developed language. None of them built anything detectable from space. There is something here that deserves more than a passing glance. The category of intelligent, language-using, tool-making organisms is not merely a category that happens to have one member. It is a category that, in the richest and most biologically diverse biosphere we know of, has exactly one member, despite hundreds of millions of years in which the relevant cognitive architecture was biologically available. This is the kind of data point that should make us at least consider the possibility that intelligence of our specific type is not a natural, inevitable product of biological complexity. It may be a remarkable singularity arising from a specific configuration of pressures and contingencies that was no more likely to repeat on Earth than it was to occur on a world without any nervous systems at all. Each one. That is the important word. The problem is not that we lack candidates for the filter's location. The problem is that we have too many. The filter might be abiogenesis, it might be eukaryogenesis, it might be multicellularity or sex or predation, or the vertebrate nervous system, or language. It might be a combination of several of these, a set of transitions each individually unlikely, whose joint probability is so small that their simultaneous occurrence on a single world is a virtually unrepeatable event. This is the rare Earth hypothesis, articulated in detail by paleontologist Peter Ward and astronomer Donald Brownlee in their 2000 book. The argument holds that Earth is not typical of habitable planets. It is anomalous. It has a large moon that stabilizes its axial tilt and drives tidal cycles that may have been crucial for early life's emergence in tidal pools. It has plate tectonics, which recycles carbon and maintains the chemistry of the atmosphere within a habitable range. It orbits in an unusually quiet region of the galaxy, far from the dense stellar populations and associated radiation fields of the galactic core. It has Jupiter in its outer solar system, a gravitational bully that deflects many potentially catastrophic asteroid impacts. Take any one of these factors away, and the probability of a biosphere resembling Earth drops substantially. Remove several of them, and the probability becomes vanishingly small. The rare Earth hypothesis suggests that the effective number of truly Earth-like worlds, not merely worlds with liquid water, but worlds with the full suite of physical and geological properties that enabled the specific evolutionary history of complex life, is extremely small, perhaps far smaller than optimistic estimates suggest. This is one answer to the silence, a deeply comforting one if you are willing to accept it. But here is where the investigation takes a turn that is harder to digest. Because the rare Earth hypothesis, however compelling, is not the most disturbing answer to the Fermi paradox. It says, we are rare. It says, the filter was in the past, improbably large, but safely behind us. It says, the silence is the expected output of a universe in which the conditions for complex life are extraordinarily uncommon, and we happen to be one of the exceptions. This is unsettling, but it is a settled kind of unsettling, the discomfort of isolation, of being alone in a vast and indifferent cosmos. That is a feeling humans have learned to manage. It is the feeling that drove Copernicus and Kepler and Galileo, the cold understanding that we are not at the center, not the purpose, not the intended audience of the universe. We have absorbed that feeling before. What we have not absorbed, what many researchers believe we have not even begun to reckon with seriously, is the alternative. The possibility that the filter is not behind us. The possibility that the silence is not the record of life's improbability. The possibility that the silence is the record of something that happens to civilizations after they reach exactly the stage we have reached now, among the first, or among the very few to have gotten this far. Standing at the base of a wall we have not yet seen. This is the possibility we turn to next. There is a class of proposed explanations for the Fermi paradox that does not require the filter to be biological. These explanations do not argue that life is rare, or that complex life is rare, or that intelligence is rare. They argue instead that civilizations exist, perhaps many of them, but that they are, for reasons we have not yet fully understood, invisible to us. These are the so-called non-detection hypotheses, and they range from the philosophically interesting to the genuinely disturbing. Some of them, examined carefully, dissolve under scrutiny. Others survive. And the ones that survive are not, in the end, particularly comforting. The most famous of the non-detection hypotheses is sometimes called the zoo hypothesis, proposed by MIT radio astronomer John Ball in 1973. The idea is straightforward. Advanced civilizations are aware of us, but they have chosen not to make contact, treating Earth as something like a nature preserve or a sociological experiment in progress. They watch. They do not intervene. Their silence is deliberate and sustained. This sounds, at first pass, like a reasonable explanation. It has something of the comforting quality of being noticed, of existing in a universe that contains watchers, even if those watchers keep their distance. The textbook answer for many people who encounter the Fermi paradox casually is some version of this. They are out there, they know about us, and they have simply chosen not to call. But here's what that explanation doesn't account for, and what almost nobody thinks through carefully enough. The zoo hypothesis requires perfect coordination across all advanced civilizations, across all of cosmic time. Not one civilization in the billions of years available has broken ranks. Not one rogue individual within any civilization has transmitted a signal our way. Not one civilization has collapsed the consensus and decided to make contact, or has been replaced by a successor civilization with different values, or has been so fractured by internal disagreement that at least one faction chose disclosure. The zoo hypothesis requires a level of universal, sustained, flawless agreement on a policy of non-contact that has no analog in any civilization we know, including our own. On Earth, no secret of comparable importance has ever been kept perfectly by more than a handful of people for more than a few decades. The zoo hypothesis posits that the secret has been kept perfectly by potentially millions of civilizations over billions of years. The improbability of this coordination is, if anything, larger than the improbability of the filter itself. It replaces one mystery with a deeper one, a variation on the theme. The planetarium hypothesis, proposed in a 2001 paper by Stephen Baxter, suggests that what we perceive as the universe is a simulation or controlled environment, constructed specifically to make us believe we are alone. This hypothesis is, by design, unfalsifiable. It cannot be tested. It explains everything and predicts nothing. It is the intellectual equivalent of a door that opens in every direction, completely flexible, completely empty of content. We note it for completeness and move past it. There is another class of explanation that is darker, more internally consistent, and significantly harder to dismiss. It was not proposed by a Western scientist. It was developed in large part through the science fiction writing of Liu Cixin, a Chinese engineer and author, in a series of novels beginning in 2008. But the logic behind it is not fiction. The logic behind it is game theory. And game theory, unlike fiction, does not care about our feelings. The dark forest hypothesis, inspired by game theoretic logic, portrays the universe as a perilous environment where civilizations stay silent to avoid attracting hostile actors. The core argument is this: any sufficiently advanced civilization can be assumed to have two properties. First, that it desires to survive, and second, that resources in a finite universe are, ultimately, limited. Given these two properties, any civilization encountering another faces a fundamental uncertainty. It cannot know with certainty whether the other civilization will remain benign, whether it will expand, whether its values will change, whether it will eventually become a competitor for resources that matter. The cost of being wrong, of trusting a civilization that later becomes hostile, is potentially civilizational extinction. The cost of acting first, of eliminating another civilization preemptively, is the removal of that uncertainty. Under the logic of this reasoning, the rational strategy for any civilization that discovers another is not contact. It is the concealment of its own existence and elimination of the threat once discovered. The universe, under this hypothesis, is a dark forest. Every civilization is a hunter, moving silently through the trees, careful not to make a sound. Because if you make a sound, another hunter will find you. The silence we observe would be, under this interpretation, not the silence of an empty universe, but the silence of a universe in which every intelligent species that has learned the rules of the game has gone quiet, terrified of the consequences of being heard. This is the most disturbing non-detection hypothesis of all. Because if it is true, our century of radio broadcasts, our television signals, our radar pulses, our deliberate METI transmissions have already announced our presence. We have already broken the first rule. We are already, in the dark forest metaphor, making noise. And if the forest is not empty, something may already be listening. Some researchers dismiss this hypothesis on the grounds that truly advanced civilizations would not feel genuinely threatened by a primitive species like ours. That the game theoretic calculus changes when one player is so far ahead of the other that elimination is trivially easy and therefore not worth prioritizing. Others argue that the distances involved make any aggressive response so slow as to be irrelevant on civilizational timescales. Still, others point out that the hypothesis requires every civilization to have independently arrived at the same game-theoretic conclusion, which seems unlikely. The honest position, the intellectually rigorous one, is that we do not know. We cannot know from our current vantage point whether the forest is empty or occupied, silent or predatory. The non-detection hypotheses each explain the silence, but none of them can be confirmed. And some of them, if true, carry implications that are not merely academic. Stay with this for a moment, because the weight of what we are discussing is easy to slide past. We are, as a species, in the position of having just learned to shout in a dark place whose occupancy we have not confirmed. We shouted before we knew the rules. We shouted before we knew what, if anything, might hear us. And now, decades into the era of radio astronomy and deliberate messaging, we are beginning, only beginning, to ask whether the silence around us is the silence of an empty room or the silence of held breath. The possibility of the filter lying ahead of us, the possibility that is hardest to contemplate and most important to examine, requires a careful analysis of what civilizations, like ours, typically do once they reach technological capability. And the uncomfortable truth is that this analysis does not require speculation about alien psychology. It requires only that we look honestly at our own. Consider the sequence of technologies that human civilization has developed in the past 2 centuries. In 1905, Albert Einstein published his special theory of relativity. In 1939, Leo Szilard and other physicists understood that uranium chain reactions could release energy on a catastrophic scale. In 1945, the first atomic bomb was detonated at the Trinity test site in New Mexico, and within weeks, 2 cities were destroyed. It took 40 years from Einstein's equations to nuclear weapons. It took roughly 1 lifetime from theoretical physics to civilizational scale destructive capability. The trajectory since then has not slowed, it has accelerated. Synthetic biology now allows the modification of viral and bacterial genomes with tools available in any well-equipped laboratory. The ability to engineer pathogens of unprecedented lethality is no longer confined to state-level actors. It is, increasingly, within the reach of small groups and, in principle, within the reach of individuals. Climate systems, pushed past certain thresholds by industrial emissions, may enter self-reinforcing feedback loops that no subsequent human action can reverse. Artificial intelligence, developing at a pace that consistently surprises the researchers building it, raises the possibility of systems whose goals and capabilities exceed human oversight in ways that are not immediately apparent. Each of these technologies shares a common property. It provides catastrophic capability before it provides adequate governance. This is the asymmetry that defines the technological phase of civilizational development. Knowledge accumulates faster than wisdom. The ability to destroy outruns the ability to protect. And the window of vulnerability, the period between acquiring the capability to self-destruct and developing the institutional and cultural maturity to manage that capability safely, may be narrow. It may be very narrow. It may be so narrow that statistically, across many civilizations, most do not make it through. If advanced civilizations usually eradicate themselves via some sort of technology run amok, such as malevolent artificial intelligence, nanotechnology, or a doomsday machine, humanity is already more than capable of destroying itself via global thermonuclear war. And sadly, it's possible that such extinction events are virtually inevitable throughout the cosmos. This is, in many ways, the most plausible location for a future great filter. Not because self-destruction is inevitable, it may not be, but because the probability of self-destruction, summed across many civilizations, each navigating a period of profound technological risk, might be high enough to explain the silence. If even 9 out of 10 technological civilizations, or 99 out of 100, fail to survive their own technology, the universe would look almost exactly as we observe it, rich in the conditions for life, scattered with planets where chemistry organized itself into biology, biology organized itself into intelligence, intelligence organized itself into technology, and then stopped quietly at the precise moment that the silence requires. The timing would be perfect for the silence. The timing would be terrible for us. This is not a mere hypothesis. We have direct evidence from our own history that the margin is thin. On October 27, 1962, a Soviet submarine named B-59 was operating in the Atlantic Ocean near Cuba, cut off from all communication with Moscow for several days, and under depth charge attack by American destroyers enforcing the quarantine. The submarine's captain, Valentin Savitsky, believing he was under attack and that war had already begun, ordered the nuclear torpedo to be armed and fired. The launch required authorization from 3 officers. 2 agreed. 1, Vasily Arkhipov, the submarine's flotilla commander, refused. Archipov's refusal is the reason that the Cuban Missile Crisis did not end with nuclear exchanges that would, by most estimates, have killed hundreds of millions of people and potentially triggered a nuclear winter incompatible with organized civilization. 1 man, 1 decision. 1 occasion on which the logic of escalation was interrupted by the judgment of a single individual in a submarine at depth. The margin between civilization and catastrophe in October 1962 was 1 person. Consider how many such moments may have occurred in civilizations across the galaxy. Consider how many may have lacked their Arkhipov. The great filter argument developed by Hansen and Bostrom suggests that we are in one of the most dangerous periods of any civilization's development, the narrow window between technological capability and institutional maturity. There is also, lurking beneath the self-destruction hypothesis, a softer variant that deserves attention. Not extinction, but stagnation. Not the dramatic end of a civilization in fire or plague or collapse, but the quiet end of a civilization that simply stops growing, stops reaching, and turns its attention permanently inward. Some researchers have proposed that advanced civilizations might reach a point at which the returns on expansion decline dramatically, where virtual environments provide richer subjective experiences than physical exploration, where the energy cost of interstellar travel becomes a reason to stay rather than go, where the social or political dynamics of long-lived civilizations favor stability over expansion. Under this view, the silence is not the aftermath of catastrophe. It is the product of contentment. Civilizations reach a level of development at which the galaxy holds nothing more attractive than what they have already built at home. In 2021, the concepts of quiet, loud, and grabby aliens were introduced by Hansen and colleagues. The proposed loud aliens expand rapidly in a highly detectable way throughout the universe and endure, while quiet aliens are hard or impossible to detect and eventually disappear. If loud civilizations are rare, as they appear to be, and the evidence strongly suggests they are, then quiet ones are also likely rare. But whether civilizations end with fire or with silence, the result is the same. The universe remains empty of detectable intelligence. The quiet civilizations that choose to stay home are just as absent from the sky as the ones that destroyed themselves. From our vantage point, the two look identical. Which brings us to a question that is, perhaps, the most vertiginous one in this entire inquiry. Is there a way to determine, from inside a civilization, which future awaits it? Is there a way to tell whether the filter is behind or ahead, without waiting for the answer to reveal itself in the catastrophe or the silence? There may be, and the answer involves looking very carefully, not at the stars, but at ourselves. Roughly 1,400 light-years from Earth, in the direction of the constellation Cygnus, there is a point in space that holds a particular importance for everything we have been discussing. It is the location of Kepler 452, a star almost identical to our own Sun, in mass, temperature, and luminosity. Orbiting that star is Kepler 452b, confirmed in 2015 by NASA's Kepler Space Telescope mission team, led by John Jenkins at the NASA Ames Research Center in California. The planet is approximately 60% larger than Earth, orbits in the habitable zone of its star, and receives roughly the same amount of energy from Kepler 452 as Earth receives from the Sun. It has been called, in popular coverage, Earth's older cousin, because its star is approximately 1.5 billion years older than ours. 1.5 billion years older. That means that if Kepler 452b developed life on a similar timescale to Earth, if the sequence of abiogenesis, eukaryogenesis, multicellularity, intelligence, and technology unfolded at a comparable rate, whatever civilization might exist there today would be 1.5 billion years more advanced than we are. They would have been where we are now, at the early technological stage, capable of radio astronomy and nuclear weapons and synthetic biology, approximately 1.5 billion years ago. And they would have had 1.5 billion years since then to either survive that phase or not. We observe no signal from Kepler 452. We observe no megastructures. We observe no infrared excess indicating massive energy capture. We observe nothing. This either means they failed to survive, or they are among the quiet ones, or they are here in some form we cannot recognize, in some dimension of activity too subtle or too alien for our instruments to detect, or the planet never developed life at all. We cannot know which. This is the second epistemological wall, not a wall of insufficient data, a wall of irreducible uncertainty. The observable facts of Kepler 452b's existence and the silence from its direction are consistent with every scenario from cosmic tragedy to cosmic transcendence. The data does not discriminate. But here is why this matters so much, and why Kepler 452b, this quiet, sun-warmed world 1,400 light-years away, functions as a mirror for everything we are examining. Every world in the habitable zone of every sun-like star in the galaxy is, potentially, a Kepler 452b. There are tens of billions of such worlds in the Milky Way alone. Each of them is a data point. Each of them is silent. And the silence taken in aggregate, is one of the most informative signals in science. Not because it tells us what happened, but because it constrains what could have happened. If even 1% of habitable worlds develop life, and if even 1% of life-bearing worlds develop intelligence, and if even 1% of intelligent species survive their technological phase, we are still talking about millions of civilizations in the Milky Way alone, over the course of its 10 billion-year history. Millions. And the aggregate activity of millions of civilizations over billions of years should be visible. It is not. The silence of Kepler 452 is the silence of every potential civilization on every potential world in every direction we have looked. And it speaks, in its aggregate, of something that does not merely explain a puzzle. It speaks of something that may define the boundary of what intelligence can achieve, and of whether the boundary has already been reached, invisibly by everything and everyone that came before us. There is, in this investigation, a place where the argument touches something much older than science, something that precedes the Drake equation by centuries, that precedes radio astronomy by millennia, that belongs to the domain not of physics, but of philosophy and psychology, and the deepest structures of human self-understanding. It is the question of what we fundamentally believe about our place in the universe. For most of human history, the answer to that question was simple and stable. We are at the center. Not merely geographically. The Copernican revolution displaced us from the geographic center 5 centuries ago. But teleologically. We believed, and in many ways still instinctively believe, that the universe has some orientation toward us. That intelligence is not an accident, but an outcome. That complexity builds toward awareness because awareness is the point. The Fermi paradox and the great filter that follows from it challenge this belief at its root. The Fermi paradox highlights the puzzling contrast between the high probability that advanced extraterrestrial intelligence should exist and the complete lack of conclusive evidence for it. If the filter is ahead of us, if intelligence routinely destroys itself at our current technological stage, then intelligence is not the universe's destination. It is the universe's mistake. A self-terminating pattern that chemistry occasionally falls into and then corrects. A temporary departure from the long, cold, stable equilibrium of dead matter, brief and bright, and then gone. This is not a comfortable thought. It is not supposed to be. But it is also not despair if you look at it carefully. Because the alternative, the possibility that the filter is behind us, that we are among the first, that the silence means not that intelligence ends here, but that we are the beginning. That alternative carries its own weight, its own responsibility, its own immensity. If we are truly early, then we are not at the end of the story. We are the story's opening sentence. If we are alone, or nearly so, then every question that intelligent life might ever ask, every discovery, every work of art, every philosophical insight, every scientific breakthrough depends on our survival. The universe has, against overwhelming odds, produced a mind that can look back at itself and wonder. That is either the prelude to something extraordinary, or it is the flash before the ordinary returns. We do not know which. We are inside the story, unable to see the ending. The evidence constrains, but does not determine the answer. And this irresolvable uncertainty, this standing at the threshold without the ability to see past it, is where the investigation must pause before it can move to its deepest questions. Take stock of where we have traveled. We have mapped the non-detection hypotheses, the explanations that do not require rare life, but rather argue for hidden or silent life. and found that most of them, examined carefully, do not resolve the paradox so much as deepen it. The zoo hypothesis requires impossible coordination. The dark forest hypothesis, unsettling in its game-theoretic logic, may explain the silence, but places us in a position of having already broken the rules. And the self-destruction hypothesis, the most plausible, the most personal, the most uncomfortable, asks us to look not at alien civilizations, but at our own trajectory, and ask honestly whether the margin between technological capability and civilizational collapse is wide enough to cross. We have visited Kepler 452b, 450 light-years away, and found the same silence there that we find everywhere. We have noted that the silence of one world, multiplied across the tens of billions of potentially habitable worlds we have identified, constitutes one of the most statistically powerful signals in the history of science. Now we turn to the inner architecture of this problem, to the question of whether the filter, wherever it lies, can be mapped precisely enough to tell us something actionable about our own future. Stand on a hilltop somewhere on Earth tonight and look up, not with a telescope, just with your eyes and the darkness and whatever patience you can bring to the act of simply looking. The stars you see are, by cosmic standards, your immediate neighborhood. The vast majority are within a few thousand light-years. The Milky Way stretches above you, that pale smear of accumulated light, containing somewhere between 100 billion and 400 billion individual suns. It is immense beyond ordinary reckoning, and it is, in its observable behavior, completely quiet. Now consider the picture we have built, layer by layer, over everything that has preceded this moment in our exploration. We began with an observation. The universe is silent. We established that the silence is genuine and deep, not merely a limitation of our instruments. We built the Drake equation as a framework for estimating how loud the universe should be, and found that every well-constrained parameter in that equation points toward a universe that should be full of detectable civilizations. We introduced the great filter as the logical resolution of the paradox. Some step in the chain from chemistry to civilization must be extraordinarily improbable. We examined the candidate steps: abiogenesis, eukaryogenesis, multicellularity, intelligence, language, and found that each one is a genuine candidate, and that we cannot currently determine with confidence which one is the filter, or whether the filter is a single catastrophic step or a combination of many moderately improbable ones. We considered the non-detection hypotheses, the zoo, the dark forest, the stagnation scenarios, and found that most of them either require implausible coordination across all intelligent life in the universe, or carry implications that are themselves deeply disturbing. We arrived at the question of whether the filter lies behind us or ahead, and we found that this question, simple in its phrasing, devastating in its implications, cannot currently be answered. Now we turn to the evidence. What clues does the universe actually give us right now about the filter's location? And what do those clues, taken seriously, imply about the civilization that is currently examining them? The most direct observational constraint on the great filter's location comes from the systematic absence of what physicists and astronomers call technosignatures, detectable evidence of technological activity at interstellar or intergalactic scales. The search for technosignatures has expanded dramatically in scope and sensitivity over the past decade. The Breakthrough Listen program is the most comprehensive and systematically designed search for extraterrestrial technosignatures to date, encompassing both radio and optical domains, and leveraging a global network of leading telescopes, custom digital instrumentation, and advanced data analysis pipelines. Initiated in 2015 as a 10-year, $100 million initiative, Breakthrough Listen aims to conduct a full census of electromagnetic technosignatures across the local Milky Way and accessible extragalactic volumes, with an emphasis on reproducibility, open data, and methodological rigor. The results, after years of observation, are consistent and unambiguous. Upon algorithmic processing, correlation of signal characteristics with known radio frequency interference populations, and extensive visual inspection, researchers found no compelling evidence of technosignatures. And this is not merely a failure to find subtle signals. The constraints are increasingly stringent. Results suggest that fewer than roughly 0.1% of stellar systems within 50 parsecs possess the type of transmitters searched in this survey. Null results set the most stringent upper limits to date on the prevalence of high-power artificial transmitters in the universe. But consider what this actually means. The absence of high-power transmitters among surveyed stellar systems is not merely an upper limit on the number of civilizations broadcasting at our level of technology. It is an upper limit on civilizations broadcasting at any level detectable from interstellar distances. A civilization even modestly more advanced than ours, by a few centuries, let alone millions of years, would, if it chose to broadcast, produce signals several orders of magnitude more powerful than anything we currently emit. The silence encompasses not just our technological equals, but everything up to and including civilizations of extraordinary capability across the surveyed volume. Some researchers respond to this by noting the limits of the survey's completeness. Jason Wright at Penn State estimated that if the world's oceans represented every place and wavelength we could search for intelligent signals, we have, to date, explored only a hot tub's worth of it. This is a fair point. The survey space is genuinely vast, and our sampling of it is genuinely small. The silence of what we have searched does not guarantee the silence of what we have not. But the argument from completeness has a ceiling. The universe has been producing stars and planets for 10 billion years. The Milky Way has had time for civilizations to arise, develop, expand, and, if they chose expansion, to colonize every stellar system in the galaxy many times over, even at speeds far below the speed of light. The absence of detectable megastructures, of infrared excess from Dyson sphere-type energy harvesting, of large-scale engineering visible in galactic morphology, these absences are not the absences of a survey that has missed 99% of its targets. They are structural absences. They suggest that galaxy-spanning civilizations of the kind that 10 billion years of development might be expected to produce are not present in the Milky Way. The absence is not a sampling artifact. It is a fact about the galaxy's history. And when we extend the survey beyond the galaxy, the conclusion does not soften. In a recent paper, members of Breakthrough Listen presented the results of their radio technosignature search of the centers of 97 nearby galaxies, joined by colleagues from the SETI Institute and researchers from the Institute of Space Sciences and Astronomy at the University of Malta, and the International Center for Radio Astronomy Research at Curtin University, published in the Astronomical Journal. Upon algorithmic processing, correlation of signal characteristics with known radio frequency interference populations, and extensive visual inspection, they found no compelling evidence of technosignatures. 97 galaxies. Each contains billions of stars, each surveyed for evidence of the kind of high-power engineering that a civilization billions of years old might produce. Nothing. The silence, at this scale, is not a puzzle of sensitivity. It is a fact about the distribution of intelligence in the universe. And then there is the evidence from the James Webb Space Telescope. Newer, more complex in its implications, and in some ways the most unsettling contribution to this question in recent years. Mere weeks after it began observations, JWST found galaxies in the very early universe that initially appeared far more massive than our theories predicted, requiring an explanation, though more recent work suggests that accreting black holes may have made some of these galaxies look bigger and brighter than they actually are. The new observatory was revealing far more bright galaxies in the early universe than anyone predicted, and astrophysicists have more than one explanation for the puzzle. The early universe, it appears, assembled structure faster than our models predicted. Stars formed earlier, galaxies matured more rapidly, and the timeline for the development of planetary systems suitable for life may extend further back than previously thought. This has a direct implication for the Fermi paradox. As astrophysicist Stephen Finkelstein at the University of Texas at Austin noted, as more data came in, it became clear that the abundance of early bright galaxies was higher than theorists had predicted. If large galaxies were present and mature earlier than expected, then the window for the development of life-bearing planetary systems extends further into the past. Civilizations could have had more time than we previously calculated. The silence, given more time in which to be broken, is correspondingly harder to explain. Some researchers think the JWST findings complicate the models of galaxy formation without fundamentally challenging the Fermi paradox. It has become clear that the standard cosmological model is resilient. Instead of forcing researchers to rewrite the rules of cosmology, the JWST findings have astronomers rethinking how galaxies are made, especially in the cosmic beginning. But rethinking how galaxies formed does not resolve the question of what happened to the civilizations that might have arisen within those earlier galaxies. If anything, it deepens the question. Here is what we know with reasonable confidence. The universe is old. It has had time. It has the materials. It has energy sources. The rules of chemistry that produce life on Earth operate everywhere. And yet the galaxy, observed with the best instruments ever built, is silent. This convergence of evidence, the null results from systematic radio and optical surveys, the absence of megastructures, the absence of any detectable large-scale engineering in the observable universe, constitutes, taken together, a body of evidence whose weight increases with every additional observation. Some researchers think this weight points toward the filter being behind us, that the silence reflects genuine biological rarity, that Earth is a statistical anomaly, that we are alone, or nearly so. Others think the weight points toward a filter ahead, that life and intelligence arise reasonably often, but that the technological phase is almost universally fatal, and that we are currently in the most dangerous interval of our civilizational existence. If our patterns of energy consumption are typical for other technological civilizations, then the lack of evidence for extraterrestrial life suggests that we may be among the first. This implies that a great filter may exist in our near future, which would mark a critical juncture of whether we become a spacefaring civilization or extinct. The evidence does not discriminate cleanly between these two interpretations. We cannot know from the outside which is correct, but we can ask a sharper question. We can ask, what would the world look like from inside a civilization approaching a future filter in the decades before it either passed through or failed? What would the warning signs be? And when we ask that question and turn to look at our own civilization honestly, the answer is not reassuring. Picture yourself in a room with a map on the wall. The map is of the entire observable universe, every galaxy, every stellar cluster, every surveyed volume. On that map, Tiny flags mark every location where we have searched for techno-signatures. The flags are clustered tightly in a small region near the center, near us. The rest of the map is blank, unsearched, unknown. Now add to the map every location where our own civilization's signals have reached. Every radio wave, every radar pulse, every deliberate transmission. The signals travel at the speed of light, and we have been broadcasting for roughly a century. At the speed of light, 100 years of broadcasting produces a sphere of signal 100 light-years in radius, a bubble in the map's scale, so small it would be invisible to the naked eye. Our presence in the universe, signaled by our technology, extends across a region that, compared to the Milky Way alone, is negligible. We are new. We are small. We are loud, in the sense that we have been broadcasting without restraint, but our loudness extends only to our immediate neighborhood. And we are, by the standards of the problem we are examining, extraordinarily young. This youth is both our vulnerability and, potentially, our hope. We are young enough that the filter, if it lies ahead, may not yet have closed. Young enough that the choices we make now, about nuclear weapons governance, about the development of artificial intelligence, about climate stability, about synthetic biology, are choices that may determine whether this civilization becomes one of the data points on the silent side of the ledger or something else entirely. Consider the technologies that currently present the most credible candidates for a civilizational scale failure mode. Nuclear weapons are the most familiar. The Cuban Missile Crisis of 1962, which we visited earlier through the lens of Vasily Arkhipov's singular decision, was not the only near miss in the Cold War record. A 1983 Soviet early warning satellite falsely detected multiple American ballistic missile launches, triggering an automatic alert that required a single Soviet duty officer, Lieutenant Colonel Stanislav Petrov, to determine, correctly, that the alert was a malfunction and not an actual attack. Petrov's decision not to escalate is estimated to have had an approximately equal probability of preventing a nuclear exchange as Arkhipov's refusal 21 years earlier. 2 individuals, 2 decisions, 2 moments at which the margin between civilization and catastrophe was measured in the judgment of a single human mind. The nuclear danger has not diminished since the Cold War. The number of nuclear-armed states has increased. The command and control systems that mediate between detection and launch have been updated, but the fundamental vulnerability, the possibility of miscalculation, misread data, or a deliberate first strike under escalating tension, has not been eliminated. There are currently an estimated 12,000 nuclear warheads in the world's arsenals, with enough combined destructive power to alter the climate of the entire planet. The weapons exist. The organizational systems governing their use are imperfect. The political contexts in which they might be used have, in several regions of the world, become significantly more unstable in the past 2 decades. This is one candidate for the filter, the nuclear window, the period during which a civilization possesses the capability for nuclear self-destruction, but has not yet developed the institutional architecture to guarantee against it. If most civilizations fail to navigate this window, the silence makes sense. Planets where intelligence arose, where technology developed, where the mathematics of nuclear fission was discovered, those planets are silent for the same reason the others are silent. The filter closed around the nuclear moment. But there is a second candidate, newer, faster developing, less well understood, that some researchers consider potentially more dangerous than nuclear weapons, precisely because the timescales of its development are so compressed that governance has no realistic chance of keeping pace. artificial intelligence. The theoretical physicist and cosmologist Stephen Hawking, in interviews before his death in 2018, suggested that the development of artificial general intelligence could be the most significant and most dangerous event in human history, either the best thing to happen to our species or the worst, with no guarantee of which. The philosopher Nick Bostrom at Oxford University has developed, over many years of work, the argument that an artificial superintelligence, a system whose cognitive capabilities exceed human-level performance across essentially all domains, would not automatically share human values, and that the problem of aligning such a system's objectives with human welfare is both critically important and genuinely unsolved. Some researchers think this concern is overstated. They argue that sufficiently capable AI systems will, by the nature of their learning processes, develop values compatible with human flourishing. That intelligence and benevolence are not merely compatible, but convergent. Others think the concern is understated, that the difficulty of value alignment is so deep, and the potential capability of advanced AI systems so vast, that the risk is not merely plausible, but probable, and that the timescales available for solving the alignment problem are shorter than is generally appreciated. What is not disputed is the speed. The capabilities of the most advanced AI systems have improved at a rate that surprised essentially all researchers in the field when measured against their prior predictions. Systems capable of sophisticated reasoning, creative production, and autonomous decision-making across a wide range of domains. Systems whose capabilities would have been considered the product of decades of additional development as recently as 10 years ago, are now in operation and in widespread use. The next decade's capabilities cannot be predicted with confidence. The decade after that, even less so. If artificial general intelligence represents a filter, if the development of autonomous, goal-directed systems whose objectives diverge from human welfare is, across the space of technological civilizations, nearly inevitable once the technology crosses a certain capability threshold, then the silence we observe may be the record of what happens when that threshold is crossed without adequate preparation. Perhaps advanced civilizations usually eradicate themselves via some sort of technology run amok, such as malevolent artificial intelligence, nanotechnology, or a doomsday machine. Not through dramatic conflict necessarily, but through a gradual redirection of resources and decision-making authority towards systems whose objectives are misaligned with the survival and flourishing of the biological intelligence that created them. This is a speculative scenario. We cannot confirm it. We cannot even observe it in action elsewhere in the galaxy. What we can observe is our own civilization's trajectory, the pace at which these technologies are developing, the degree to which governance is keeping pace, and the historical record of what happens when civilizations acquire catastrophic capabilities faster than they develop the wisdom to manage them. The historical record is not comforting. There is a line of reasoning that brings all of these threads together: the Fermi paradox, the great filter, the techno-signature silence, the candidates for a future filter, into a single, coherent, and deeply sobering argument. It is an argument that, once understood, makes the universe feel permanently different. And it is an argument whose logic, though simple in structure, has implications that extend well beyond the question of whether we are alone. The argument is this: we observe a universe that should, by all statistical expectation, be loud with intelligence. It is not. The silence is genuine, deep, and increasingly well constrained. The silence implies a filter, something that dramatically reduces the number of observable civilizations relative to what simple probability would predict. That filter is either behind us or ahead of us, If it is behind us, we are extraordinarily fortunate, and the universe is ours to explore. If it is ahead of us, we are currently at or approaching the point at which something ends. Something ends for almost everyone who reaches it. Now add one more piece of evidence, one more observation, newer than any of the ones we have discussed, and in some ways the most personally confronting. We are developing right now, at this specific moment in civilizational history, the precise categories of technology that are the most plausible candidates for a future filter. Nuclear weapons, developed. Synthetic biology capable of engineered pandemics, in early stages, advancing rapidly. Artificial intelligence approaching general-purpose cognitive capability, actively in progress. Climate systems being pushed toward tipping points, measurable in real time. We are not approaching the filter from a distance. We may be standing at its base, and our window for navigating it safely, the window between developing these capabilities and developing the maturity, governance, and institutional architecture to survive them, is not measured in geological time. It is measured in decades. Robin Hanson, writing in 1998, framed this with characteristic precision. The great filter ahead of us, if it exists, would not necessarily look like a sudden catastrophe. It might look from the inside like a sequence of perfectly normal decisions, each individually defensible, that collectively add up to a trajectory from which recovery becomes progressively harder. The filter might not feel like a filter. It might feel like business as usual, right up until it doesn't. And here, in this argument, we reach the place where the investigation stops being about the universe and starts being about us. Pause here, because what follows represents the deepest implication of everything we have built. The universe is empty. We have established this. We have worked through the most rigorous available explanation for its emptiness. We have arrived at the great filter and examined it from every angle currently accessible to human reasoning. And the conclusion, the unavoidable, logically inescapable conclusion, is that one of two things is true. Either the path from chemistry to civilization is so extraordinarily difficult that we, here, on this particular planet, orbiting this particular star in this particular galaxy, have beaten odds so vast that they dwarf any lottery ever devised by human mathematics. Or the path is not that difficult, and the difficulty lies ahead. And the silence around us is not the record of a universe where life is rare. It is the record of a universe where civilizations are common, and where something reliably and repeatedly ends them. We cannot know which is true. This is not a statement of epistemological cowardice. It is the honest conclusion of the most rigorous analysis currently available to us. We have one data point, ourselves, and we are inside it. We cannot step outside to observe our own trajectory from the perspective that would make the answer clear. What we can do, what the logic of the problem demands that we do, is ask, with full seriousness, what are the rhetorical questions that the universe is posing to us right now by its silence? Is the silence telling us that we are alone and therefore responsible? The only keepers of everything intelligence has ever achieved or might ever achieve? Is it telling us that we are in danger and therefore required to treat the next century not as normal history, but as the decisive interval of civilizational survival? Is it telling us that the filter is something we cannot yet identify, some unknown mechanism that has ended every civilization before it could become visible, and that we will not recognize until it is already operating? Is it telling us that the universe is not indifferent to intelligence, but adversarial to it? That complexity at civilizational scales is something the physical or sociological laws of reality do not permit to persist? Is it telling us that the stories we tell ourselves about progress and accumulating wisdom are not borne out by the evidence, and that the emotional difficulty of confronting a genuine civilizational risk systematically prevents the civilizations that face it from responding adequately? Is it telling us something we cannot yet formulate? A truth that requires a different kind of intelligence or a different kind of courage to articulate? Is the silence, in the end, a message? And if it is, are we the audience for whom it was intended? Or are we simply the latest in a long sequence of civilizations that have reached this exact moment, read the silence the same way we are reading it now, and then, one by one, gone quiet? We cannot know. We genuinely, irreducibly cannot know. This is not the "we do not yet know of a problem awaiting better instruments." This is the "we cannot know of a question whose answer lies outside the observable evidence available to any civilization at our stage of development." The filter's location cannot be confirmed from inside the civilization that faces it. The test cannot be graded by the student taking it. This is the edge of what reason can reach, and yet the reason is not finished. Because even at this edge, even in the face of irreducible uncertainty about the filter's location, the logic of the situation demands something. Not certainty, not resolution, but a response, an orientation, a stance. Here is where everything we have discussed inverts, and the picture we have been building reveals its true character. For most of this exploration, we have been looking outward, at the sky, at the absence of signals, at the statistical structure of a universe that should be populated and is not. We have been treating the silence as a fact about others, about whatever intelligence arose before us, failed before us, vanished before us. But the silence is also a fact about us, about what we are and what we might become, and whether the next entry in the ledger reads differently from all the ones before it. Consider what it means, in full, to be the civilization that has arrived at this exact moment. We are the species that has developed, within the space of a single century, the instruments to ask whether we are alone, the science to understand why the answer to that question is so disturbing, and the technology to make the answer permanently moot in either direction, by destroying ourselves or by becoming, eventually, the kind of civilization whose absence from the sky currently constitutes evidence against optimism. We have developed the capacity to end the question by ending ourselves. We have also, in principle, developed the capacity to answer the question by surviving. The two possibilities are not symmetric in their implications. One closes the ledger, the other opens it onto everything that intelligence might ever ask, discover, create, and become, across timescales that make the current age of the universe seem like a preface. The silence around us is not merely data, it is a constraint. It tells us that the path from where we are to where a truly long-lived, galaxy-spanning civilization might stand is narrow, and that the vast majority of whatever has tried to walk it has not arrived. It tells us that optimism about civilizational survival is not the default expectation of a universe operating at full statistical scale. It tells us that the comfortable assumption that of course we will survive, that of course progress continues, that of course the problems currently accumulating at the base of the technological phase will resolve themselves through normal institutional processes, is not supported by the available evidence. And here is where the picture inverts most completely. Here is the thing that, once seen, makes the universe look different forever. The silence is not a message about the past. It is a question about the future. Specifically, it is a question about our future, And the extraordinary, almost unendurable strangeness of our position is that we are the first generation in the history of this civilization to understand the question clearly enough to formulate it. The first generation with the scientific framework, the observational data, the theoretical architecture, to look at the silence and understand with reasonable confidence what it is asking. Every previous generation of humans who looked at the night sky did so without knowing what the stars were, without knowing how many there were, without knowing that most of them have planets, without knowing that the chemistry of life operates everywhere, without knowing about the Drake equation, the Great Filter, the Fermi paradox, or the systematic absence of technosignatures across a surveyed volume of billions of galaxies. We are the first to hear the silence for what it is. And that fact, the fact of being first to understand, is either a terrible burden or an extraordinary privilege. It may be both. It is certainly not nothing. The universe is empty for a reason. We have spent this exploration working through what that reason might be. And now, at the deepest point in the argument, we arrive at the possibility that is most vertiginous of all. The reason may not be fixed. The reason may be contingent. The reason may be, in part, a consequence of choices made or not made by civilizations that reached exactly our stage and faced exactly our decisions. If that is true, if the filter is not a wall but a test, not an obstacle but a question, then the silence is not a verdict. It is an invitation to be the exception, to be the civilization that, having understood the question, manages to answer it differently from everything that came before. Picture yourself standing outside on a clear night, somewhere far from city lights, somewhere that still has genuine darkness. Perhaps the high desert of New Mexico, near the Very Large Array, those 27 white dish antennae arranged across the plain of San Agustin, pointing at the sky with the patience of objects built for waiting. Or perhaps the Karoo Plateau of South Africa, where the Meerkat telescope array stretches across dry scrubland in a ring of metal flowers, each one listening. Or perhaps simply a field somewhere, any field, with grass under your feet and the full weight of the Milky Way overhead. The temperature has dropped. You can feel it on your forearms, on the back of your neck. The air is still. The stars are not twinkling, as they do near the horizon where the atmosphere is thick. Up high, they are steady, hard points of light, each one a sun, each one ancient, each one burning through chemistry we have now fully understood and named. Stay here for a moment. Do not move forward yet. Just breathe and look, and let the weight of what we have been examining settle around you like the cold. The argument has been long and demanding. It has required holding several difficult things in mind simultaneously. The statistical enormity of the universe, the biological improbability of intelligence, the logical structure of the Great Filter, the vertiginous possibility that the filter is not behind us, but ahead, the personal implication that the next decades of this civilization's existence may be the most consequential in the history of life on Earth. That is a heavy architecture to carry, and the mind, confronting it honestly, needs space before it can absorb the full weight. So, breathe, look up, let the field around you be simply what it is, dark and quiet and very old. The silence of the sky above you right now is the same silence we have been discussing. This is not a metaphor. The actual sky over your head is the same sky that Enrico Fermi looked up at, the same sky that Frank Drake aimed his radio telescope toward in Greenbank, West Virginia in 1961, the same sky that the Breakthrough Listen instruments are scanning tonight with instruments of extraordinary sensitivity. And it is still quiet. The data arriving at those instruments right now, tonight, as you stand in your field, is consistent with a universe that contains no other civilization, sending a detectable signal in our direction. That fact, that the sky above your field and the sky above the radio telescopes are the same sky, and that both are silent, is worth sitting with. Breathe in. There is something about the specific quality of cosmic silence that no description fully captures until you have felt it directly. The sensation of standing under an enormous sky and understanding, not merely intellectually, but physically, that the distance between you and the nearest star is so vast that the light you are seeing left its source years before you were born. In some cases, decades, in some cases, centuries. The light you are receiving from the star Deneb, bright in the summer sky, left its source somewhere between 1500 and 2600 years ago. By the most commonly cited estimates, roughly when Aristotle was alive, when the Persian Empire was a functioning political entity, when no one on Earth had any concept of what a star was. That light has been traveling toward you, uninterrupted, for 24 centuries. And when it reaches your eye tonight, it completes a journey that began before the Roman Republic, before the Great Wall of China, before the construction of the Parthenon. The universe does not hurry. Its timescales are not our timescales. Its patience is not our patience. And in all that time, in the tens of billions of years that stars have been burning, and planets have been cooling, and chemistry has been organizing itself into increasingly complex arrangements, we have heard nothing. No signal has arrived from across those distances that cannot be explained by natural processes. No pattern has emerged from the noise that requires the existence of a mind to explain it. The universe, in its observable behavior, has produced exactly one confirmed instance of a civilization capable of asking why the universe is quiet. 1. Rest with that number. Not the hundreds of billions of galaxies, not the hundreds of sextillions of planets, not the 10 billion years of cosmic history, just the one. The single confirmed data point that stands against the silence, the only voice in the record that is definitely asking, rather than simply being. You. Standing in a field, or lying in a bed, or sitting somewhere still and dark, listening to these words. You are, as far as the current evidence confirms, part of the only civilization in the observable universe that has ever looked at the sky and understood what it was seeing well enough to ask why no one answers. That is not a small thing to be. There is a particular quality of feeling that arrives when you hold this thought with complete honesty and without flinching away from it. A feeling that is not quite awe, not quite grief, not quite wonder, but a compound of all three that has no exact word in the English language. The Japanese have a phrase, mono no aware, that points in this direction. The bittersweet awareness of impermanence, the beauty that comes specifically from the knowledge that beauty will end. The universe's silence has something of that quality. It is beautiful in its way. It is the universe's way of confirming the rarity of what you are. And it is terrible in its way for exactly the same reason. The silence does not care about us. This is important to understand clearly. The universe is not watching our civilization with anything resembling anticipation or concern. The physics of the universe do not have a preference for our survival. The laws of nature that govern the behavior of nuclear warheads and engineered pathogens and misaligned artificial intelligence systems will operate with complete indifference to whether the civilization that developed those technologies chooses to manage them wisely. the indifference is absolute. And yet, somehow that absolute indifference is not the same as abandonment. Because the universe's indifference also means that there is no cosmic force aligned against our survival. There is no predator waiting at the edge of the filter, no external agent of destruction, no intentional adversary, no law of nature that specifically targets intelligence and dismantles it. The filter, whatever it is, operates through us, not upon us from outside. It is made of the same material we are made of, the same chemistry, the same physics, the same evolutionary tendencies toward short-term thinking and competitive behavior, and the underweighting of long-term risk. The filter is not a wall built by an alien engineer. It is a wall we may build ourselves, without quite realizing what we are constructing. This is, in its way, both the most disturbing and the most hopeful conclusion of the entire investigation. Disturbing because it means the danger is intimate, not cosmic, not external, not something we might hope a more advanced civilization would warn us about in time. It is here, in the choices being made now, in the institutions that govern nuclear arsenals and biotechnology and artificial intelligence and carbon emissions, in the difficulty of coordinating global responses to civilizational scale risks in a world organized around the sovereign competition of nation-states. Hopeful, because it means the answer is also here, in the same place, in the choices, in the institutions, in the possibility, not the certainty, but the genuine possibility, that a civilization that understands the problem clearly enough might respond to it differently than the ones that preceded it. Let the field stay quiet around you for another moment. The stars above you are the same stars that were above every civilization that ever arose and fell on Earth. The Sumerians and the Egyptians and the Romans and the Han Dynasty and every other human civilization that built something extraordinary and then, in time, became archaeology. Each of them, in their moment, believed themselves to be engaged in something unprecedented and durable. Each of them was right about the unprecedented part and wrong about the durable part. Each of them eventually became the past tense. The difference, the one difference that distinguishes our current moment from all those previous civilizations, is not wealth or technological capability or cultural sophistication. It is this. For the first time, a civilization on Earth has developed the capacity to understand, in physical and statistical terms, the conditions under which civilizations end. Not through mythology or prophecy or cultural intuition, but through science, through the accumulation of evidence, through the kind of reasoning that begins with an observation. The sky is silent and follows the logic wherever it leads. We are the first civilization on Earth to be able to read the silence. That is either the most important thing that has ever happened in the history of this planet, or it is the last interesting thing that will ever happen here. The choice, and it is a choice distributed across billions of individuals and thousands of institutions, and the accumulated decisions of the next several decades, is ours. The field is quiet. The stars are steady. The silence is the same silence it has always been. Now we look at what that silence means in its final and most honest dimension. There is a historian named Arnold Toynbee who spent most of his professional life, from the 1930s through the 1960s, studying the rise and fall of civilizations. Not one or two, but 23 of them, in exhaustive comparative detail. His monumental 12-volume work, published between 1934 and 1961, was an attempt to identify the structural patterns common to civilizations as they developed, flourished, and declined. Toynbee's framework was not predictive in the scientific sense. He was a historian, not a physicist. But his central observation has a peculiar resonance when placed beside the Fermi paradox. Toynbee argued that civilizations do not fail because of external forces. They fail because of internal breakdown, specifically because their institutions lose the capacity to respond creatively to challenges that are novel relative to the institutional architecture developed to handle previous challenges. The challenge arrives. The institution responds with the solution that worked last time. The solution does not fit the new problem. The mismatch compounds over time. The civilization degrades from within. He called this the failure of the creative minority, the small fraction of any civilization's population that generates the new ideas and institutional adaptations that allow a society to navigate genuinely novel problems. When that creative minority exhausts itself or is replaced by a merely dominant minority that enforces old solutions on new problems, the civilization begins its long descent. Toynbee's framework is not the whole truth. Historians have critiqued it extensively, and the civilizations he studied are a small and culturally specific sample. But the structural pattern he identifies, the mismatch between the speed at which novel challenges arrive and the speed at which institutional responses can adapt, maps with troubling precision onto the situation we find ourselves in. The challenges we currently face, nuclear proliferation, climate destabilization, pandemic risk, artificial intelligence governance, are genuinely novel. They are novel in scale, novel in mechanism, novel in the degree to which their consequences are potentially irreversible. The institutional frameworks developed to manage previous iterations of human conflict and technological development. The Treaty of Westphalia, the United Nations Security Council, the Non-Proliferation Treaty, the Biological Weapons Convention, were designed for a world in which the relevant destructive capabilities were held by states, moved slowly, and produced consequences reversible enough to allow course correction. In the world currently developing, those conditions do not all hold. Some of the most dangerous capabilities are migrating towards sub-state actors. Some of them develop on timescales of years rather than decades. Some of their consequences, once initiated, are irreversible on any timescale relevant to human civilization. The institutional architecture is not keeping pace. This is not a pessimistic claim. It is an observation about a structural condition that can be changed, and that many people within those institutions are actively working to change. The Non-Proliferation Treaty has prevented nuclear weapons from spreading as widely as many analysts feared in the 1960s. The Montreal Protocol of 1987 demonstrated that global governance of a civilizational scale risk, the depletion of the atmospheric ozone layer, is achievable through coordinated international action, even when the economic costs of the required changes are real and the affected industries are powerful. Climate science, over the past 3 decades, has produced an unprecedented degree of international scientific consensus and has driven, however imperfectly and incompletely, a measurable shift in global energy policy. The track record is mixed. The momentum is uncertain. The timescales are compressed. And it is precisely this mixture, the genuine evidence of human capacity for civilizational scale coordination, set against the genuine evidence of our current institutional inadequacy for the most novel and most dangerous challenges, that makes the question of the filter so intensely personal. We are not spectators of this question. We are its subject matter. Consider what this means in its full dimension. The great filter, if it lies ahead of us, does not arrive as a single dramatic event. It arrives as the accumulated product of many decisions Decisions about weapons, about technology, about governance, about the degree to which the humans who understand a risk are able to communicate that risk effectively to the humans who make the relevant decisions. It arrives in the gap between scientific understanding and political action. It arrives in the difficulty of coordinating global responses to global risks in a political system that rewards short-term thinking and punishes the kind of intergenerational responsibility that civilizational survival requires. In other words, the filter, the most plausible version of a future filter, looks from inside like a policy problem, like a governance problem, like a coordination problem. It looks from inside like the ordinary friction of institutions trying and partially failing to manage genuinely hard challenges. It does not look from inside like the end of everything. That is the deepest horror of the scenario. The filter does not announce itself. It compounds quietly, the way that small decisions about nuclear safety or biosafety or AI development standards or carbon emissions accumulate into trajectories whose final destinations are not visible from the point at which the critical decisions are being made. This is why the silence is disturbing in the way that it is, not because it implies a dramatic cosmic catastrophe, but because it implies a quiet, accumulated, institutionally mediated failure that may not be recognizable as failure until it has already occurred. The same failure repeated across the galaxy on every world that reached the technological threshold and found it impossible to govern. Hansen's original framing contained a phrase that deserves its own moment of attention. He noted that the filter's location in our future would mean that humanity's prospects of reaching interstellar colonization are bleak, not impossible, not certain to fail. Bleak. The word is precise. It does not mean hopeless. It means that the light is poor, the path is narrow, and the obstacles are real. Bleak is a condition you navigate. Hopelessness is a condition you accept. The difference matters. There is a parallel, ancient and instructive, that exists in the human record of civilizational near misses. Moments when the accumulated weight of institutional failure, technological danger, and political miscalculation came within the thickness of a single decision of producing an irreversible outcome. We have visited two of them already, Arkhipov in the submarine, Petrov at the radar console. There is a third that belongs here, not because it is more dramatic, but because it illustrates a different dimension of the problem. In January 1995, a Norwegian scientific rocket launched from the Andoya Space Center on a research mission to study the aurora borealis, lit up Russian radar screens in a pattern indistinguishable from the initial trajectory of an American submarine-launched ballistic missile. The Russian nuclear briefcase was activated. President Boris Yeltsin, for the first and only time in Russian history, opened the nuclear authorization case and prepared to issue a launch order in response to what appeared to be an incoming attack. The situation resolved when the rocket veered northward on its actual research trajectory, and the anomaly was recognized for what it was. The window in which civilization hung on the correct interpretation of a radar return was approximately 8 minutes. 8 minutes. 3 documented near misses. 3 moments when the margin between civilizational survival and civilizational catastrophe was measured in minutes or in the judgment of a single person. And these are only the documented ones, the incidents that became known through declassified records or eventual disclosure. The full count of moments at which nuclear catastrophe was avoided by institutional luck rather than institutional design may be considerably higher. Now extend this observation to the full range of civilizational scale risks currently in play. Biological risks, The probability that a natural pandemic or an engineered pathogen could produce casualties of sufficient scale and speed to destabilize the complex supply chains and institutional functions on which modern civilization depends. Climate risks. The probability that certain physical tipping points, the collapse of the West Antarctic ice sheet, the destabilization of permafrost carbon stores, the disruption of the Atlantic meridional overturning circulation, could be crossed in ways that are not reversible on any timescale relevant to civilization as currently organized. AI risks. The probability that the development of autonomous systems with goals misaligned from human welfare could redirect the resources and capabilities of civilization in ways that are difficult or impossible to correct. Each of these risks is contested in terms of its probability and timeline. Some researchers think each of them is manageable with adequate institutional response. Others think some of them approach near certainty given current trajectories. The disagreement among genuinely expert researchers is genuine and should be represented honestly. What is not contested is the structural property that each of these risks shares with the nuclear near misses. They all involve a gap between the speed of the threat's development and the speed of institutional adaptation. They all involve consequences that are at least partially irreversible if the adaptive response arrives too late. And they all require a degree of international coordination that has, historically, been achieved only under conditions of shared crisis, which is to say, often too late. The filter, if it lies ahead, looks like this. It looks like a convergence of manageable risks that are not managed, for the ordinary reasons that important things are not managed: competing short-term interests, institutional inertia, the difficulty of coordinating across sovereign states, the systematic underweighting of low-probability catastrophic events in both individual and institutional decision-making, and the peculiar human tendency to believe that the serious problems belong to the future, while the present is always somehow still the comfortable prologue. The universe's silence is the record of how this tends to end. But it is only a tendency, not a law. And here, finally, is where the investigation arrives at the place it has been building toward since the first word of this exploration. The silence is a record of the past. What the future holds is not yet determined. The ledger is not yet closed. The next entry has not been written, and the civilization currently capable of reading the silence, the only civilization currently confirmed to be capable of reading the silence, is also the only civilization currently in a position to write a different kind of ending. The burden of that position is real. The uncertainty is real. The danger is real. The margin is narrow and may be narrower than it appears from inside. But something else is also real. Something that the silence, for all its weight and all its warning, cannot erase. The fact of being here. The fact of having made it this far through 4 billion years of biological accident, through the single improbable event of eukaryogenesis, through the lucky configuration of a large moon and a stable star and a planet in the right zone at the right time, through the contingent evolutionary path that produced, in one lineage among millions, the kind of cognition that asks questions about the universe rather than merely responding to it. The extraordinary, improbable, almost certainly unrepeated chain of events that produced a civilization capable of asking why the universe is empty. That is not nothing. That is, measured against the silence, something so rare that it may approach the singular. It is either the beginning of the story or the story's last sentence. The choice, not final, not made, not irreversible, tilts toward which direction the next page turns. Stand in that field one last time. The stars are where they were. Deneb burns in the north, its light 24 centuries old. The Milky Way spreads overhead in its pale, unhurried arc. The instruments at Greenbank, West Virginia, and at the Karoo Plateau in South Africa, and at the Meerkat Array, and at every other facility currently scanning the sky, are still listening. They have been listening all through this exploration. They will listen tomorrow. They will listen for years and decades to come. And whatever they return, silence or something else entirely, will be one of the most important facts our species has ever collected. For now, they return to silence. Take stock, one final time, of the path we have walked together. We began with an observation so simple it fits in a single sentence. The universe is silent, and it should not be. From that observation, we built a careful, layered picture of what the silence actually means, starting with the statistical framework that makes the silence strange, working through the biological history that makes intelligence rare, or possibly singular, arriving at the great filter as the logical response to the paradox, and examining, with as much honesty as the evidence allows, where in the chain from chemistry to civilization that filter most plausibly lies. We spent time with the Drake equation, that elegant 1961 framework from Frank Drake's meeting at Greenbank, the framework that laid bare, for the first time, the full scope of what would need to be true for the universe to be as empty as it appears. We found that the early terms of the equation, now well constrained by decades of exoplanet surveys and stellar observation, point insistently toward a cosmos rich in potentially life-bearing worlds. We found that the late terms, the biological and civilizational ones, remain after 60 years of careful thought almost completely unconstrained. We examined abiogenesis, the origin of life from non-living chemistry, and found it to be one of the most consequential unknowns in all of science, a process whose probability, drawn from a sample size of exactly 1, spans estimates ranging from near certainty to near impossibility, depending on which assumptions one accepts and which one rejects. The Miller-Urey experiment of 1953 showed that organic molecules form readily. The gap between organic molecules and a self-replicating cell, the work of researchers like Lee Cronin at Glasgow, continues to illuminate, remains profound and unresolved. We spent time with eukaryogenesis, the single unrepeated transition documented by Lynn Margulis beginning in 1967, from simple prokaryotic cells to the complex eukaryotic cells that are the architectural foundation of all animal life. We noted, with the weight it deserves, that this transition happened once in 4 billion years. We considered what a universe full of prokaryotic life, biologically active, chemically rich, permanently invisible to our instruments, would look like from the outside, and found that it would look exactly like what we observe, a universe that appears empty. We visited Nick Bostrom's careful articulation of why the discovery of life on Mars, the seemingly triumphant moment that would be, in public framing, the greatest scientific discovery in human history, would actually constitute an omen. The closer the discovered life to our own complexity, the more it would shift the probability toward a filter that lies ahead rather than behind, and the darker the implication for our own future. We walked through the non-detection hypotheses, the zoo, the dark forest, the stagnation scenarios, and found that each of them, examined with genuine rigor, either requires coordination across cosmic scales that has no plausible mechanism, or carries implications at least as disturbing as the alternatives it proposes to resolve. We noted the game-theoretic logic of the dark forest with the seriousness it deserves, and observed that our century of radio broadcasting has already, under that logic, made noise in a forest whose occupancy we have not confirmed. We examined the techno-signature evidence from Breakthrough Listen, the most comprehensive search in history, covering 97 nearby galaxies and 1 million nearby stellar systems, returning null results that set the most stringent upper limits ever placed on the prevalence of high-power artificial transmitters anywhere in the observable universe. We noted that the James Webb Space Telescope, revealing unexpectedly mature early galaxies that formed before our models predicted, effectively extends the window of civilizational development further into the past, making the silence correspondingly harder to explain away with appeals to insufficient time. We traced the candidates for a future filter with painful specificity: the nuclear near misses, Arkhipav's refusal, Petrov's correct judgment, Yeltsin's nuclear briefcase opened and then closed, each one a moment at which civilization's margin proved to be the width of a single decision. The synthetic biology risk, developing faster than its governance frameworks. The artificial intelligence transition, whose capability growth has consistently outpaced the predictions of the researchers building it. The climate tipping points, whose irreversibility, once crossed, removes the possibility of course correction on any timescale meaningful to living people. We noted, honestly and without softening, that these risks share a common structural property. They all involve a gap between the speed of the threat and the speed of institutional adaptation. They all involve consequences that are at least partially irreversible once the threshold is crossed. And they all require international coordination of a kind that human history has achieved, when it has achieved it only under conditions of recognized shared crisis, frequently just barely in time, and sometimes not at all. We stood in Arnold Toynbee's framework and recognized our own moment in his pattern of civilizational challenge and institutional response. The pattern in which the creative adaptation that survives the challenge is not guaranteed, but is also not impossible, and is always the product of choices made by specific people in specific institutions at specific historical moments. And we arrived, through all of this, at the deepest and most irreducible conclusion of the entire investigation. The universe is empty for a reason. The reason is not yet fully known. It might be biological rarity, the possibility that the chain of improbable transitions from chemistry to civilization is so extraordinarily long, and each link so fragile that Earth is, effectively, alone in having produced it. It might be civilizational mortality, the possibility that intelligence arises reasonably often, but reliably destroys itself at the technological threshold, leaving a universe that is rich in the ruins of brief civilizations and empty of their ongoing presence. It might be some combination of both, many worlds where life never crossed the crucial biological thresholds, and the few that did, subsequently failing to navigate the technological ones. What is certain is that the reason is real, and that it operates at scale across the entire observable universe, and that we are, right now, at the stage of development that the reason most plausibly concerns. We are the stage. We are the question. We are, in the most literal and least metaphorical sense possible, the experiment. The galaxy-spanning silence that Enrico Fermi gestured at over lunch in 1950, that Frank Drake began to formally investigate in 1961, that Robin Hanson formalized in 1998 as the Great Filter, that silence is not abstract. It is the same silence that is above you right now, personal and immediate and completely real. The distance between you and the nearest star is 4 light-years of vacuum, and across that vacuum and the billions of light-years beyond it, there is no confirmed voice. There is only this one. And what that one voice does with its brief window of awareness, what this civilization, this remarkable and improbable and deeply endangered civilization chooses to do with the understanding that it is almost certainly alone in its moment and possibly alone in its existence? That is the question the silence has been asking all along. It is not a question that despair can answer. Despair looks at the silence and concludes that the ending is already written, that the filter is inevitable, that the outcome is fixed. Despair is not only emotionally corrosive, it is logically unjustified. The silence tells us the filter is real. It does not tell us that we have already failed to pass it. The verdict is not in. The ledger is not closed. It is also not a question that false comfort can answer. The easy reassurance that of course we will survive, that of course intelligence finds a way, that of course the arc of history bends toward continued complexity, is not supported by the available evidence. The arc of civilizational history, written across the silence of billions of galaxies, bends toward quiet, toward the ending of signals, toward the return of dead physics. What answers the question, if anything does, is something in between despair and false comfort. Something harder to name and harder to sustain than either of those easier postures. Something that looks at the silence honestly, acknowledges its weight, its implication, its genuinely disturbing content, and then turns back to the present moment and asks, what, given all of this, is worth doing next? The answer to that question is not provided by cosmology or astrobiology or the Fermi paradox or the Great Filter. The answer to that question is provided by the choices of specific people in specific institutions, by the degree to which the understanding of civilizational risk percolates through the political and technological systems that govern the capabilities most likely to function as a filter, by the degree to which the generation currently alive, the first generation in history to understand the silence clearly enough to read it, chooses to treat the next several decades not as normal time, but as consequential time, extraordinary time. The kind of time that, looking back from a future that survives it, will be recognized as the interval in which everything was at stake, and the margin was narrow, and the outcome was not guaranteed. And some aggregate of choices and institutions and individual moments of clarity and courage was enough, or was not. The 2 trillion galaxies overhead, the hundreds of sextillions of planets silent in their orbits, the deep null results from the most sensitive instruments ever built. All of it points to the same conclusion, the same question, the same invitation. The universe is empty for a reason. What that reason is, in the end, may depend on what we do now. If this changed how you see the silence above you, if the stars look different tonight, heavier with implication and richer with the strangeness of our position among them, then the time we spent together was well spent. Thank you, genuinely, for staying through the full weight of it. The question deserves the attention you gave it. The sky is still there. The silence is still there. And so are we. For now, improbably, and by the narrowest of margins. That is enough to begin.